Hello and welcome back. We're going to spend some time in session 2 now, focusing on the part-whole relationship of fractions. So, a quick reminder, credit due to West Yorkshire Maths Hub, particularly Sam, the Assistant Maths Hub Lead, who supported me in designing these courses, and also to the NCETM for contribution of resources, and it's a great place for you to go and find good stuff. Okay, so we're just going to remind you again of the 5 big ideas of the Teaching for Mastery. Remember that the aim is to get these things in your mind, stuck in your mind: representation and structure, mathematical thinking, fluency, variation and coherence. Separate CPD training session if you want a little bit more detail, but remember to get all these things going through everything you're thinking about in maths teaching. Another reminder as well about the thinky face. If you see this pop up during the CPD session, we're going to particularly focus on those questions or ideas, things that you've done, things that you're thinking about when we come to our next live session. So do make sure you write some particular notes or have particular thoughts about those slides. Okay, so in the last session, we looked at fractions in the curriculum. We thought about what a fraction could be, and that's what we really focused on: what a fraction was made of, what it conceptually was, and how to illustrate that. This session, we're going to spend the whole thing just concentrating on the part-whole relationship, and we'll look at comparison, ordering, equivalence, and using it in problem solving, bar modelling with fractions as a particular illustration in the next session. Okay, so what's the problem with fractions? Well, fractions are different to natural numbers. Natural numbers you can count with 1, 2, 3, 4, 5, etc. Those are natural numbers. They're amounts of things. There are 7 things, there are 2 things, 3 things. I can count 1 thing, 2 things, 3 things, 4 things, 5 things, and so on. But fractions are different in that they are relative to other things. They are relative to the whole. Okay, so it can be an amount, of course, we discussed that in the last one, but it's relative to a whole. A half, I can count in half, but that half is relative to the concept of 1, to that whole. So let's take a look at this question here. Would you rather have 1/4 of £20 or 1/2 of £5? So we should always be looking at that part-whole relationship. What do you think about that question? Should be the fraction of what? What is the whole? So would you rather have 1/4 of £20? So in that case, the £20 is the whole. 1/2 of £5, the £5 is the whole. And we can explore what the answer to that might be. It's always in relation to that whole number. So we're going to focus on fractions as part of a whole. It is a hugely important concept, and it is found to be the easiest element of fractions to be understood by children. It's also obviously very important, but it doesn't mean that's the only thing. But it's hugely vital for that conceptual understanding and that basis of knowledge. Okay, so there are 4 things we need to think about as teaching points when addressing this aspect of a fraction, this part-whole relationship. So one first part is that any element of the whole is the part. It doesn't matter how much of the whole we take. Doesn't matter what it looks like, doesn't matter what shape it is, doesn't matter if it's food, if it's pictures, if it's numbers, doesn't matter any of those things. All that matters is the relationship as there is an element of the whole, any part of the whole. A whole can be divided into equal or unequal parts, and it's really important that we address this as a misconception of what a fraction can be. When we're talking about fractions, we're talking about dividing a whole into equal parts, and it's really essential that we address that, because of course you could have an unequal part of a whole, but that's not the same thing. So the relative size of the parts can be compared. If we had one whole, I divided it into 3 parts, and then I have another whole, so maybe another pizza maybe, and that's been divided into 4 parts, I can then compare the size of these 2 parts. And that comparison then leads us to understanding. So the 1/3 of the pizza, if I divided that into 3 parts, is greater than the 1/4. I would get more pizza from the 1/3. And a 4th element to look at is the iterative element of the parts of a whole, and we looked at that briefly last time as well. If you know that one of the equal parts, and you know how many of them there are based on the denominator, then you can construct the whole. So if you're presented with a piece of a bar of chocolate and you know that that is 1/10 of the chocolate, or you know that there are 10 equal parts, you can reconstruct that chocolate bar. You can see what it looks like and see how much of the whole it's related to. So as we progress through fractions in primary school, we come to the question of a common denominator. So this is about understanding what the whole is and appropriately generalising. It's about unitising. So we've got an example here to help. 2 sheep and 3 goats is how many sheep? Well, of course, that doesn't make sense. There are still 2 sheep. Doesn't matter if I add 3 goats on. The number of sheeps is still the sheeps. Sorry, the number of sheep is still the same. How many sheep are there altogether? Well, there are 2. Let's think about this differently. Instead of saying sheep, how about we have 2 sheep plus 3 goats is how many animals? How many animals are there altogether? So we're unitising, we're taking all of those different things and we're giving them a different group. So we're saying that they are all animals. They are all the same thing in that particular way, and that's related. It's a common denominator. So here we've got an example. It's a really common example you'll come across if you go on various mastery training courses. Here's a map of China. We can think of it as, here's the whole country of China. If China is the whole, Shanghai is a part of the whole, and we can look at the idea of that part-whole relationship. It's so important that fractions are introduced in a concrete example, a real-life example that's contextually relevant to the children. So showing them a map of China might not be the best one for our children, but giving them that rooting in a concept that they are familiar with. Related to that, how about this one? Does anybody know any places in Europe? Can they use a stem sentence to express the whole and the part? And you could do a you say, we say. So we could, of course, say if Europe is the whole, then France is a part of Europe. Or if Europe is the whole, then the United Kingdom is a part of Europe. Or if Europe is a whole, then Italy is a part of Europe. And we can repeat that part-whole relationship, that stem sentence. You say, we say, that sort of thing. I say, you say. So I want you to have a go at this activity. I think if 8 is coming up soon, so do actually do this activity because it will help you with that. So, equal parts. Take a square piece of paper. Get a piece of paper, make it a square. Okay? I want you to divide it into 4 equal parts. We say that each part is equal. So do that. Get your piece of paper. We should have a piece of paper in 4 equal parts. So we say that each part is equal. How can we prove that? Can you prove that concept using the model that you've just made? So what I want you to do is think about that. Pause the video and consider those questions. Can you prove it? Can you use your model to prove it? Can you think of a different way to divide the square into 4 equal parts? And I'd like you to share your examples and have a conversation of that proof at the live session next. Okay, have a look at these shapes and consider what you notice about them. They're different shapes. They're all divided into 4 parts. Now I'm going to move them around a little bit. How have I sorted them? What do you notice about how the shapes have been organised? Equal parts and unequal parts. On the left-hand side of the shape, we've got shapes which have been divided into 4 equal-sized parts, and on the right-hand side, we've got the shapes which have been divided into 4 unequal-sized parts. When we're talking about fractions, we're focusing on the equal parts of a whole, not just any part. They are equally sized parts, and it's important that you use these non-examples as well in mathematical concepts to highlight that misconception and show what it definitely is not. Interestingly, what do you notice about the shapes which have been divided into equal parts? Not all the parts look the same. Are they all equal though? they're all equal to each other, of course, within that same amount. The 4 equal parts in the circle are all equal to each other. The 4 equal parts in the triangle are all equal to each other. Interestingly, you've got two quadrilaterals there. The 4 equal parts in the square are equal to each other. I wonder if when you divided the square into 4 equal parts, you did it differently. Do your equal parts look the same as those ones or differently? When we look at the rhombus, which is, in essence is a square, then it's been divided up differently. So you've got joining the diagonal lines there. So I've got 4 triangles essentially. Are they still equal parts? Interesting concept. Okay, so this is part of a sequence of lessons that was taken from one of the NCETM sequences. Are these three equals? Take these 3 equally sized squares. Are all the parts equal? So the parts, if you took one part out of the square on the left and one part from the square in the middle and one part from the square on the right hand side, would all those be equal? Prove it. And what would you say? What would you expect your pupils to say? Chances are they're going to say no. They often do, don't they? But of course they are equal because each of the squares has been divided into 4 equal parts. So even though they look different, they are equal. So have that conversation. The whole has been divided into equal parts. The whole has been divided into unequal parts. Which of these sentences applies to this model? Have the wholes been divided into equal parts or have they been divided into unequal parts? Of course, they've been divided into equal parts, so we can say the whole has been divided into 4 equal parts. Here we've got the parts again. Here's one part of that first square. Here's one part of the middle square. And here's a part of the third square. What makes this such an important question? Even though they look different, they are equal in relation to the area of the whole. And because all of the wholes are equal, of course, they are all equal. How about this one? What's changed? What's the same? What's different? A fantastic question to develop some reasoning skills within your class to get lots of really great mathematical conversation. What's the same? What's different? Well, of course, it's no longer a square. We're now looking at a triangle. What's the same? Well, it's still divided into 4 equal parts. So having a look at the sentences again, which of the 2 sentences applies, have a discussion with that. Of course, the correct one is the equal parts. The triangle has been divided into 4 equal parts. Now let's take a look at this one. Are the parts equal or unequal? What would you say? Prove it. What would you say? How would you prove? How would you explain whether or not the parts are equal or unequal? What do you expect the children in your class might say when asked to prove that question? So which of the sentences is the appropriate STEM sentence to match this particular example? Remember that looking at these non-examples is really important. It's vital to show them these unequal parts as well as the equal parts so they can grasp that concept in their head. Oh yeah, so these ones are unequal parts. These wholes have been divided into 4 unequal parts. Now the idea of part-whole infractions can be looked at in 2 different ways. Using single shapes as part of a whole object, such as these, or using a set of discrete objects as part of many. When doing this, we must use real-life discrete objects to experience fractions as a quotient model and consider how this links to division. So I've got 4 things and I'm going to divide it by 2. For example, identifying half the cherries as the same as dividing the number of cherries by 2 is important. Identifying a third of the cherries is the same as dividing it by 3, etc. Note that the part of a whole can be different shapes, could be wholes, could be quantities, could be different shaped wholes, could be different sized wholes, could be amounts. Okay, so when we're looking at those shapes, that part of a whole thing, we can look at it in lots of different ways. Let's take a look at these four things. Here in this first question, what fraction of the shape is shaded? So you might have a discussion here about the relationship between numerator and denominator, depending on what stage you are in there. So here we've got a circle that's divided into 3 equal parts. So that shows me the denominator is 3. That's how many parts it's being divided into. Remember to use the word equal. And I've also got 1 out of the 3 parts shaded. Or should I be writing 2 out of 3 to illustrate the number of parts not shaded, the number of white sections rather than the orange section? Again, in the second bar, I've got 2 parts of the whole, and 1 of them is shaded in. In the, I don't know, let's call it a flower. I could say it's been divided, it's got 4 of these oblongs, 4 of these ovals, sorry, and 1 of them is shaded in. I could say that the part of the pentagon has been divided into 5 equal parts, and I've got 1 of those. What's the same and what's different about them? Oh, they've all got 1 part shaded in. What's different? They all have different numbers of parts, different equal parts in their whole. So in the circle there are 3, in the pentagon there are 5, in the bar there are 2. So we can have that conversation. What about the next one? Tick or cross to show which fraction, if this fraction is shaded. So in the circle, is a quarter of the fraction shaded? Is 1/5 of the fraction shaded in the bar? Is 1/3 of the fraction shaded in the triangle? Is a quarter shaded in the bar at the end? And that's about exploring some of these different ideas. In that circle, what are the misconceptions we might gather? Of course, there are this misconception based around the unequal and equal parts. It'd be really interesting to see if they just said, well, none of them, they're all wrong. But what about the bar at the end? Is that divided into a quarter? That's an interesting idea. So look at what some of those misconceptions could be. What kind of language could you get from them? How about this one? What fraction of the set is circled? So in the first set, 1/3, 1 out of 3 sticks. In the second set with the dumplings, 1/4 of the set, and we can start now to relate the idea to maybe fractions of amounts, and in the third set 1/2. Circle the correct fraction of each set. So we've got a quarter, we've got a 1/5, we've got a 1/6. How do each of these models apply to the different types of fractions we've been exploring, we've been looking at? How do each of them relate to the part-whole relationship? What kinds of things would you generate from this? What kind of discussions would you have with your children? Out of curiosity, take a look at that bottom right example again. And let's take a look at the oranges. Now, there are 5 columns of oranges there, so expect them to draw a circle around 1 column of 3 oranges, yeah? What if they didn't? What if they circled 3 random oranges? Is that correct? Would you be happy with that? Would you not be happy with that? Would it require some sort of conversation? Would it require some sort of discussion? Let's take a look at these 2 worksheets. I'm going to look at the differences between them. So the first one has been arranged so that the items are dead simply able to divide them because they are looking for half, and they've been arranged so that you could essentially draw a dotted line down the centre of the page and it would easily divide them in half. Do you think this is helpful? Is there an appropriate stage for this to happen in the learning? Or is this leading them? Is it guiding them? Is it not really helping them to demonstrate their conceptual understanding? Take a look at the second one. So the second one has a different concept. This one uses horizontal and vertical lines to divide the shapes. But this one introduces the idea of the non-concept, the equal or unequal. So whilst each one has a line, not all of them have been divided equally. So we have the examples of not a half. Which of the 2 sheets do you prefer and why? Do you think both of them have a place in their learning? Which one do you think promotes greater thinking, greater understanding? Which one do you think helps to make connections? Which one do you think is a more effective representation? Why do you prefer that one? Okay, so before we finish off, let's take a quick look at this activity that came from a sequence on the NCETM website. There are also videos on YouTube or Vimeo showing Caroline Ainsworth, who's a mastery specialist, working with children using Cuisenaire rods. So today, the pink rod is the whole. How would you describe the remaining rods? I think that's a fantastic activity. Dead simple, it could be something you just start your lesson with. Your pink rod is a whole. What's the red one? Well, the red one's a half. What about the white one? Well, the white one's a quarter. What about the light green? 2/3 perhaps, and obviously this will depend on their understanding of Cuisenaire and how they relate to each other. It's a great activity to start to develop that understanding and might lead into our next session. So, just a quick reminder, that's the end of this particular session, and we will be moving on to comparing and ordering and contextualizing fractions in the next session, and also looking at bar modelling as one particular pictorial representation of fractions and how we could use that in the classroom. See you next time.